So now we're going to talk about our next topic, which is blocking in affine programs in the polyhedral framework. So let's consider this program, which is for I equals 0 to n, for j equals 0 to n, some statement S. And the statement S could have accesses to data elements that involve I and j as indices, and depending on what the statement S is, there will be some data dependencies between different iteration points in this polyhedral space defined by the two-dimensional polyhedron of I in one dimension and j in the other dimension. In this graph here, I'm drawing the iteration space, I being the y-axis and j being the x-axis, and this is a two-dimensional polyhedron. Let's say this is, because it's going from for I equals 0 to n and j equals 0 to n, this is actually a square polyhedron, and there are all these iteration points which are marked as blue crosses. This time the edges that I'm drawing are not the data dependence edges. The data dependence edges are kind of unknown right now because we don't know what S is. S is supposed to be a placeholder for any statement. So these yellow edges here are not the data dependence edges, but they are the execution order edges. Alright. So first, for example, 0, 0 will execute, then 0, 1 will execute, then 0, 2 will execute. When I'm basically using I, j as the way to basically represent the iteration point. So 0, 2 means I equals 0 and j equals 2. 0, 3, 0, 4, 0, 5, and when I reach the end of one axis, when I let's say reach let's say n was 6, then I've reached the end at j equals 5. Then I go to 1, 0, and then 1, 1, 1, 2, 1, 3. In fact, we have discussed this before. This execution order is identical to the ascending lexicographic order of the two loop indices I, j. Alright, so now we know that, so this is the execution order. And what is blocking going to do for us? Blocking is going to change the execution order, alright? And let's for now assume that when we do blocking, we are basically preserving the data dependencies, and that's going to be a requirement. But for now, let's just assume that, S is completely data independent or something like that. And if it is, then we can do the following. We can basically change this loop nest, which had depth 2, to a loop nest of depth 4. And in this loop nest, we still have the outer loops iterating from 0 to n, but the big change here is that instead of incrementing by 1, now I'm going to increment by a blocking factor b. Similarly, when I kind of iterate on j, I'm going to increment by b. And so I'm going to call them I and jj just to distinguish them from I and j, which I'm going to use in the inner loop. So basically the outer loops are going to hop at at an interval of b. And so they're going to first consider, for example, 0, 0, and then they're going to consider 0, b. And then they're going to maybe consider 0, 2b, and then 0, 3b, and so on, until they reach the end. And then they come to b, 0 instead of 1, 0. Here they're going to come at b, 0, and then b, b, 2b, and so on. So that's what the outer loop iteration is going to do. And the inner loop iteration is going to basically, for every block, for every such interval from 0 to b, or b to 2b, or 2b to 3b, it's going to iterate one by one on all the iteration points. So the inner loop looks like for I equals ii into b, so that's the starting point of the inner interval, going till ii into b plus 1, and because n may not be a multiple of b, so I basically take care of the boundary condition by saying minimum of ii into b plus 1 comma n I plus plus. And similarly, I do a step increment for j. I say j equals jj into b to min of jj into b plus 1 comma n j plus plus. So the inner loops are basically iterating at an interval of 1, and the outer loops are iterating at an interval of b. And the statement now is executed for inside this loop nest of depth 4. So when I do this, when the question is it okay to do this? When is it okay to do this? And even before that, what is the advantage of doing this? So I think we have already discussed the advantage of blocking when we are talking about blocking in matrix multiplication. By doing this and choosing B carefully, what we can do is we can ensure that the memory footprint of the inner two loops in this case, fit inside the cache, inside the L1 cache. And if we choose B in such a way, then basically we can increase the temporal locality and also possibly the spatial locality of the program. And we have seen this as a concrete example in matrix multiplication, where we discussed how one could block, what one could implement with this blocking transformation for matrix multiplication by hand. But let's say a compiler was to try to do this automatically. What are the conditions, and that too for a general S, right? I mean, may not be particularly the matrix multiplication statement. It could be any general statement. What should be the conditions on S under which such a transformation is legal? And that's the topic of today's module. But before we discuss that, let's look at the new iteration space pictorially, and let's kind of compare the new execution order with the previous old execution order. So the iteration space is still identical. We have, I and j, and we are going from 0 to n on j and 0 to n on I. But this time, for my first inner loop, for my first iteration of the inner two loops, this is the block. Let's say I assume b equals 3, so I'm going to go from 0, 0, 0, 1, 0, 2, and I'm going to stop there because, this is the case when II equals 0 and JJ also equals 0, right? So in the outer two loops, I have one point, which is II equals 0 and JJ equals 0. And for that, I'm going to go from I equals 0 to, this should be actually II into, II plus 1 into B. So this is a mistake here. This should be II plus 1 into B, right? Comma n. And similarly, the second one here should be JJ plus 1 into B. All right. Okay, so I'm going to, in my inner loop, I'm going to go from 0, from I equals 0, because II is 0, to I equals 3, which is because B is equal to 3. So I'm going to go from 0 till 3, but 3 is not included because it's strict less than. And so I go from 0, 1, 2. That's for I, and for j also, it's again going from 0 to 3, which is again 0, 1, 2. So I get this square of 3 cross 3, which is my single block, which is defined at II equals 0 and JJ equals 0. Now, if I look at the execution order, these orange edges basically represent the new execution order. So I first execute 0, 0, then 0, 1, then 0, 2, then 1, 0, 1, 1, 1, 2, and so on. Now I want to point out that when I do this, notice that in my original execution order, I would have executed 0, 3 after 0, 2, but in my new execution order, I'm not executing 0, 3 after 0, 2. I'm actually executing 1, 0 after 0, 2. And then once I'm done with the whole block, so once I've executed I equals 2 and j equals 2, I execute the next block, which is II equals 0 and JJ equals 1. And so that point starts here. And now I have a new block here, which is, again, this is a 3 cross 3 block starting at II equals 0 and JJ equals 2. And so this is basically this block represents the second point on the outer two loops of my loop nest. Similarly, my third loop nest is going to go to this one here. I should just erase this because actually there is a mistake here. So let me just kind of erase this code here because I think we've already corrected this in a previous slide. Then I go from here to here, and this is again a 3 cross 3 block. And so we get another 3 cross 3 block and so on, right? And basically, finally, in this toy example, they're going to be, because I chose B to be 3 and N to be 6, I basically have 4 blocks. Okay. Now, the question that I want to answer is, so first of all, the point of doing this blocking is so that I can better exploit my cache locality, and assuming that each of these blocks are basically have an access pattern such that their entire memory footprint fits in the cache, then I basically get a win. And basically, if it was true that this point here, let's say I equals 1 and j equals 0, and this point here, let's say, which is I equals 0 and j equals 2, if they were going to access the same location, for example, right, then this transformation would help us get better performance and better locality, because in the original code, the reuse distance between I equals 0 and j equals 2 and I equals 1 and j equals 0 is pretty high, because I would go all the way till the end. But in this new code, the reuse distance has decreased. And so that's the advantage of doing blocking. But the next question is, when is it okay to do this blocking? The question I want to ask is, when is this possible? All right. And so when I say when is this possible, of course I can come up with some very strict conditions on S. For example, if S was completely data independent, then this is possible, because if each iteration of S has no dependency on any other iteration, which means if I was to draw a dependency graph here, or dependency edges between different iteration points, if there were no edges, then it is always okay to do this kind of blocking. Okay. All right. So, and here's an example where it is actually not possible. If there were basically lots of dependency edges. So in this particular example, I assume that S is basically writing to A of B I comma j. So notice that B I comma j can be an arbitrary value, and if I use that as an index into an address, that basically means that each iteration point I comma j can basically access any point in A. And so basically conservatively I have to assume that there are data dependencies between every iteration with every other iteration. Okay, so basically if I was to draw dependency edges, then there will be dependency edges with all possible there will be a fully connected graph in that sense. Of course, we are restricted by the execution order. So we only draw edges from iterations that executed before to iterations that executed after. We have discussed this before, which basically means that in a 2D graph, in a 2D dependency graph, the theta, the angle of the dependency edge, can only be between 0 and 180 degrees, excluding 180 degrees. All right. Okay. So if I have this, then is this transformation valid? And the answer is no. And it's easy to see that if I look at this particular, any particular pair of points for whose iteration order is changed. So if I look at, for example, this point here, which is 0, 4, and if I look at this point here, which is 2, 1, then the iteration order of 0, 4 and 2, 1 in my original order was that 0, 4 executes before 2, 1 in my original order. But in my new order, 0, 2, 1, because 2, 1 is part of the first block, executes before 0, 4. So in my new order, 2, 4 executes before 2, 1 executes before 0, 4. And so here is here's an example of two iteration vectors I and j, such that or I1 and I2, such that I1 precedes I2 in the original order and I2 precedes I1 in the new order. And if in this example, because both of them actually have a data dependency, if they were basically, if B is 2, 1 and B 0, 4 were basically evaluating to the same value, then they would be writing to the same address. Let's say B 2, 1 was, let's say, 0, and similarly B 0, 4 was also 0. Then basically both of them are going to be writing to A0. And so the relative order matters, because if 0, 4 executes before 2, 1, I'm going to be writing a different value, and the eventual value of A0 would be different from if the order was reversed, right? And so it is not always okay to do blocking. Here's a concrete example where it's not okay to do blocking. Now, okay, so here it is not okay to do blocking, but where is it actually okay to do blocking? What is the condition under which we can say it is safe to do blocking? Well, the condition is that if the relative order of the two iteration points has changed, then there should have been no data dependence between the two iteration points. And this condition actually looks identical to the condition that we had for pipelining, which was also very similar, which said that if I precedes j in first and if I1, I2 precedes J2 in the other, then there should not be any data dependence between the two. And basically that boils down to saying that the relative order remains the same for things that are data dependent. In other words, if I was to draw the data dependence edges in my iteration space, then all the data dependence edges should have an angle or have an acute angle or a right angle. So anywhere between 0 degrees and 90 degrees, including 0 and 90. If my dependency edges if all my dependency edges have this theta, then that basically means that their relative order will not change between blocking. If you can check for yourself that if the dependency edge basically has a 90-degree angle, then the 2 points between which that dependency edge has been drawn, their relative order does not change because of blocking. So let me take some examples. These purple edges here are basically representing dependency edges. So let's look at this particular dependency edge that's going from 0, 2 to 1, 3. Now notice that this is basically, going in, it's an acute angle. So theta is basically something between 0 and 90. And we can see that the relative order between 0, 2 and 1, 3 is preserved between the original order, execution order, and the new execution order. In both cases, 0, 2 precedes, so let me just write it like this, 0, 2 precedes 1, 3, and that's true for both the original order and the new order. And actually you can take any 2 points and such that the line between them is such that the second point is basically executing after the first point, and the line between them is an acute angle, which is between 0 and 90. You would find that their relative order between the old order and the new order remains the same. Let's take a couple more examples. So let's say this was a right angle. So from 2, 2, this point, this corner of the first block, to this corner of the third block, which is 3, 2. Right? So 2, 2 to 3, 2. This is a 90-degree edge, and even these 2 points, 2, 2 and 3, 2, their relative order remains the same, which is 2, 2 executes before 3, 2. Here's another example, 2, 4 and 3, 4. Once again, even in the original order, 2, 4 was executing before 3, 4. And in the new order also, 2, 4 is executing before 3, 4. But if I take some examples where theta is greater than 90 degrees, then I'm going to find that for some of those cases, the relative order has changed. So here are some examples where theta is between 90 and 180, excluding 90 and excluding 180. And here are the purple edges that show 2 such examples. So if I look at this example, which is 0, 3 to 2, 2, then I see that first of all the theta here is basically greater than 90, and in the original order 0, 3 was preceding 2, 2, but in the new order 2, 2 precedes 0, 3. Alright, and so in this case basically whenever theta is greater than 90 degrees, I'm basically here's an example where the relative order has changed, and also it turns out that the theta is 90 degrees. I'm claiming that whenever the relative order will change, it would be only change for those cases in a 2D space where theta was greater than 90. But I also wanted to point out that it's not the other way around. It's not necessary that whenever theta is greater than 90, then the relative order will change. Alright, so the statement basically says that relative order changes only if theta was greater than 90. But it's not necessary that whenever theta is greater than 90, then relative order changes. So it's not an if and only if, it's an only if, right? And so, for example, here's an example going from 3, 3 to let's say 4, 2. Now 3, 3 to 4, 2, the angle is still greater than 90, but the relative order hasn't changed. In both cases, 3, 3 executes before 4, 2, even in the original order and in the blocking order. Alright, but we know that, for all angles which is between 0 and 90, we are pretty sure that the relative order doesn't change. And so what we can infer from that is that it's okay to block as long as all my dependency edges are such that they belong to the 0, 90 degrees range. And so here is a sufficient condition for when you can block. You can block whenever theta is, you can block whenever all the dependency edges belong to 0, 90 degree angle theta. In other words, whenever theta is greater than 90, there should be no data dependence between those two iteration points. So any two iteration points which are, and if you draw a line between them and theta was greater than 90, then it should be true that in my original program there is no data dependence in between those two iteration points. And if that condition is met, then it is okay to do blocking in that case. Alright, and this is identical, I mean this condition that we basically spelled out is identical to the condition of fully permutable loops that we also use for pipelining. And so basically what we are arriving at is that it is always possible to implement the blocking transformation for fully permutable loops. And if I look at my example of matrix multiplication where we were first introduced to blocking, notice that we have a 3-nest loop here for I equals 0, j equals 0, k equals 0 to n. All three are going from 0 to n. Cij plus equals aik star bkj. Now this is my matrix multiplication loop nest. In this case it's a 3-level loop nest, and in fact for this matrix multiplication we do a 3-level blocking, depth 3 blocking. In the example that I've been showing so far in today's module, I was only doing depth 2 blocking, but matrix multiplication is an example where we actually do a depth 3 blocking. And once again, it is okay to do, we can check for ourselves that this particular loop nest, the statement S that is part of the matrix multiplication routine, is actually causing the entire loop nest to be a fully permutable loop nest. And this can be seen that because if I and j are different, either let's take any two iteration points, let's say I1, j1, k1 and I2, j2, k2. Now if I1, j1 is not equal to I2, j2, which means either of I or j are different, then the 2 points are data independent anyway because they're only writing to different locations. And so they don't have any data dependence. First of all, the data dependence can only come from C because A and B are only being read. It's only C that's being written and also read. And so all the read after write or write after write or write after read dependencies can come only from C. Moreover, if I1, j1 is different from I2, j2, there are different locations that are being written. So if I1, j1 is different from I2, j2, then the two iteration points are data independent anyway. And so the only data dependencies are when I1 equals I2 and j1 equals j2. And so the only kind of degree of freedom here is k. I mean the only reason we could potentially have a data dependence is when, because we could have a change in order of data dependence is because we can basically change the order of k. But we can check. So the question you want to ask is this loop fully permutable? And we can check different iteration orders. And basically what will happen is either we will move k to the left, so we're moving k to the upper loop, or we move k to the really outermost loop or something like that. Irrespective of what order we choose for this iteration loop, we are going to find that the relative order of k's remains the same, right? So within a single I, j, different values of k would have the same relative order, irrespective of what permutation I choose for I, j, k. And so that basically means that because the only data dependent iterations can be the ones which have I1 equals I2 and j1 equals j2, and within those data dependent iterations, we are sure that when I'm doing blocking, forget about blocking. When I'm doing permutation of the loops, then the relative order of different ij k1 and ij k2 will remain the same, because irrespective of where I take k, the relative order is going to remain the same. That basically means that this loop is fully permutable, and because this loop is fully permutable, it is okay to block it. And so that's why blocking in matrix multiplication is a legal transformation. But also we have, now we have also know a more general condition, which is full permutability of loops, under which blocking is acceptable.